Welcome back. This time we will look at how simulation of driving cycles can be used to analyze variations in powertrain operating point during driving. To analyze the operating point, we will simulate the vehicle in QSS. In this analysis, the road gradient will always be 0. This time we use the default settings of the parameters in the vehicle model. Note that we do not do anything with the outputs of the vehicle model, and that is because the QSS model sends some results to workspace, even if we do not ask for it. We can see that by opening the vehicle model. Here we see that the 3 outputs are sent to workspace, and we can see which names the variables with the results will have. We go back to the top level of the simulation model. Now we simulate the model by pressing the Run button. Then we look into Workspace for the results. Here we can see that there are 3 variables which contain vectors with the outputs of the vehicle model. There is also a time vector t, which is generated by the driving cycle block and can be used when analyzing or plotting the results. The following plots in this video are generated from this output data. To analyze the results, we create a force speed diagram in which the operating point can be plotted. The black curve is the running resistance curve for the vehicle on a flat road, and it will be used as a reference. The speed of the driving cycle is plotted as a function of time in the lower diagram. We start by analyzing the NEDC cycle, which has been used for European certification tests. It's easy to see that it's a generated cycle, as it is far too regular for being measured from a real vehicle. A measured driving cycle is more noisy, as we will see later. The cycle has a first part representing stop-and-go driving in a city in speeds of no more than 50 km per hour, and a part at the end representing highway driving at speeds between 50 and 120 km per hour. By plotting the force and speed output of the vehicle model in the force speed diagram, we get the trajectory followed by the operating point. Looking at the full trajectory, it is difficult to see how it corresponds to the driving cycle. So, to better see that, we will look at how the operating point moves during the driving cycle. To do that, we follow how the speed varies as the red point moves with time in the lower diagram. For each point in the driving cycle, there is a corresponding operating point in the force speed diagram, which we also show with a red point. Now we will run through the cycle and stop a few times to comment what we see. Notice that each time the speed is constant, the operating point is on the running resistance curve. The higher the speed, the further to the right the operating point is. Whenever the vehicle is accelerating, the operating point is above the running resistance curve, and when it's decelerating, it's below. This means that the operating point cannot move in any direction in the diagram. In the upper part, it always moves to the right, and in the lower part, always to the left. Now we will run the rest of the cycle. Notice that the operating point is on the running resistance curve quite long time of the cycle, and only temporarily is much higher or much lower. It can also be seen that the operating point always moves in clockwise circles. Now we hope that you understand how the trajectory of the operating point relates to the speed profile of the driving cycle. To see how different driving cycles can be, we compare the NEDC cycle with the US FTP 75 cycle, which is a measured cycle. Remember these very regular trajectories of the NEDC cycle when we now switch to the results from the FTP 75 cycle. It can be seen both from the trajectories of the powertrain operating point and the speed profile that this cycle is much less regular. For instance, it can be seen that the speed is never really constant for any longer time period, and due to the bigger variation in speed and acceleration, the operating points are more spread out in the force speed diagram. By plotting the operating point trajectory, it is possible to see how the powertrain will be used during the analyzed driving cycle. The trajectory reveals some aspects which are not seen from the driving cycle speed profile, like how high and how low force is required in different speeds. This time we have shown how a driving cycle can be used together with the vehicle model to calculate the time variation of powertrain force. The result can then be plotted as a trajectory of the powertrain operating point in a force speed diagram. This trajectory summarizes how the powertrain will be used in this specific driving cycle. Now you can test what you know about how operating points vary during driving cycles.